Hello. Welcome all to this inaugural lecture hosted by University College of London. And we are very, very happy to have you all here. And in particular, we are delighted to have Professor Béatrice Baudet's family here. Vous êtes vraiment bienvenue. Ravi de vous avoir avec nous. I'm looking forward to a wonderful lecture. So before we get started, let me take care of the basics. There are no fire drills today, so if you hear a fire alarm, please walk calmly out of the building. There are two exits, one in the back, one in the front, and they will lead you to two places of safety, one in Torrington Place through the Roberts main entrance, and the other one in Mallet Place by the library. So let me start by introducing a little bit the concept of the inaugural lecture. An inaugural lecture is an opportunity that newly promoted professors have to summarize their career achievements and deliver a lecture on a subject that they choose pertinent and important that represents those career achievements. And today we are extremely honored to have Professor Béatrice Baudet, Professor of Soil Mechanics, giving her inaugural lecture. Béatrice has developed an illustrious career that has seen her engage with extensive collaborations in many countries around the world, including Brazil, France, Italy, India, and China. She joined the Department of Civil and Environmental Engineering at UCL in 2001 as a lecturer, having just submitted her PhD at City University in London. Her PhD focused on the constitutive modeling of natural clays. And at the time, when research in soil mechanics was just developing, Béatrice had the vision to promote the understanding of soils through micromechanics, a unique approach that basically was the beginning of what was to become an extraordinary career. At UCL, she expanded her work to laboratory characterization of solids, including time effects, soil reinforcement, and soil mechanics for coarse-grained solids. And for this work, she has received numerous accolades. She left UCL for a period of 6 years to hold an appointment at Hong Kong University between 2010 and 2016. And in this period, her career saw a shift in her research to investigate solids at the microscale, notably mapping the evolution of sand-grained surfaces during loading. This work was awarded in 2021 the British Geotechnical Association Medal. This award has been given since 1958, and it's a medal that is presented for meritorious contribution to geotechnical science or practice by a paper published in a leading geotechnical journal. And so it's basically the best paper of the year in that field. And later, she was invited to deliver the 2025 Bicentennial Geotechnique Lecture, and which is a biennial lecture nominated by the editorial panel of the journal Geotechnique, which is the top journal in the field. So as you can see, we are in front of an exceptionally accomplished individual. The talk that she delivered was entitled Clay Behavior Through the Keyhole, gave a new perspective on the relationship between porosity and clay properties. And it's a reference for the field. So Béatrice has served in the editorial panel of several leading journals, including 2 terms on the Geotechnique Journal Advisory Panel and as a deputy chair and editor of Geotechnique Letters. So let me finish by thanking Béatrice for being the first inaugural lecturer in many years for our department. We are all very, very, very much looking forward to it. And without further ado, please.
Okay, well, I'd like to start by thanking Jose for nominating me for this lecture and for accepting to do this introduction. So I'm going to talk about soils. Okay, this is my area of predilection, so it's not surprising. And I'm going to try to show you how today we look at soils at the microscale, which is departing a bit for what people used to do, say, 100 years ago. So, of course, I think about soils on a daily basis, maybe not at the weekend, though. And what do you think when you think about soils? So, soils, well, we may picture a nice beach with sand. Okay, sand is soil, and we may picture its particulate nature. So, sand is made of grains, and we can visualize the grains are coarser or finer, depending on which beach you are. Clay comes into the category of soils, and we can see that the aspect is very different. It looks sticky, greasy even, and definitely the particles I cannot see with my naked eye here. I think that somebody who captured very well the nature, the granular nature of soil is Seurat, with his pointillist approach. So here, if I look at the beach in Honfleur that he painted in 1886, I can see the different grains, I can almost see the different grains of soils on the beach. Okay, arguably, he also thought that the sky and the water and the buildings were granular, but never mind. So maybe why do we study soil mechanics? Well, there is a practicality that we want, of course, to help with construction. So we can think of basements, we think of tunnels, foundation. But I think that for us researchers in soil mechanics, we were very comforted by the publishing of an article in 2020 in the New York Times by a journalist called Monroe. And he said, no one understands how sand works. So we thought, okay, so other people think it is difficult. And he made this sort of diagram showing areas of physics by difficulty, and the hardest was the sand behavior. So we feel, that somebody understands what we're facing every day, trying to understand sands and clays. And I think what I try to show today is how we can approach sands and clays in similar but also different manners to try to make more sense of how they behave. He put somewhere in his article, sand is challenging in part because the grains have so many different properties like size, shape, roughness, and more. And size, shape, roughness are things that I will explore in the lecture as well. Now, geotechnical structures are not always visible. If anything, they're temporarily visible usually. So maybe that when there is a basement being made, you have a glimpse of the construction, but then it quickly disappears as the overground structure is being built. And maybe that's why the geotechnical engineer is often the unsung hero of construction, I think. So this is an example of an excavation that some of us have seen. So this is the basement of the new UCL hospital facility for cancer treatment, which is on Grafton Way at the back of the Cruciform. So now we have this grey building, but actually it houses a 15-meter basement, which has a proton beam therapy facility for acute cancer treatment. And we can imagine how the scale of those excavations in urban environment is complicated by the amount of props that are holding the walls together. There are enough facilities underground in the region, and then, of course, the building. Tunnels also are part of what the geotechnical engineer would do. And this is an example of a new tunnel building, not with a bit of controversy, I understand, between Lyon and Torino. And this is being led by Vinci Grand Projet as the engineers. Another example is foundation, and not just foundations of building, but of course we have all seen wind turbines as we drive along, and onshore there are some offshore, and the turbine, for all its beauty, has tricky foundation conditions to deal with, and that has been a subject of research for many years and is continuing, especially when you think of the turbines that are in the North Sea with all the storms and the rest. Now, not all geotechnical engineering problems are man-made or designs are man-made. We do have our own geohazard problems. So that here is an example in Hong Kong of a debris flow. So this is a debris flow on Lantau Islands, which has affected, I can't remember how this was. Which has affected the expressway to the airport. So landslides come into the category of what we may be worried about. Now for me, I know I'm supposed in those lectures to talk a bit about me, so there's just one slide. I don't like to talk so much about me, but this was not the obvious pathway. So this photo that everybody sees, which I chose for the advert, is it's got a special significance. It's not a wine glass, even though I come from Bordeaux, but Richard, my PhD student, pointed to me that my wine glass has been AI emptied for the photo. So, of course, there is a sand at the back, which is important for this lecture, but also what is also significant to me is that it was taken in Berck-sur-Mer, which is on the northern coast of France, which is where one of my ancestors, François Callot, in 1900s, created a new orthopedic institute for treating children, and this is still living to this day. It's called the Institut Callot. And in fact, if you do Google my name, you're more likely to find an article by my father, who, with Fontan, his colleagues and mentor, pioneered some heart surgery procedure I can't pronounce, or his brother, who was a reconstructive surgeon. Yes, a lot of people in my family are doctors or surgeons. But I had a grandfather who was a civil engineer. He worked in Lebanon and he worked in Morocco on this beautiful project that is the Bin Elouiden Dam, where he spent 10 years overseeing the construction. In fact, it was one of his colleagues, a geologist, Paul Lévesque, who donated to me a book, who made me sort of choose my career at a point where I was choosing between hydraulics and geotechnics. So I went from Bordeaux to London via an engineering school in Paris, a civil engineering school in Paris, an Erasmus opportunity to do a Master of Geotechnics in Glasgow University, with 3 wonderful months at La Sapienza in Rome, where all these then postdocs have become established professors and they're friends now. Then I joined City University, a brilliant, vibrant group at the time in geotechnics, where I got the best possible training. Then UCL with a small interlude in Hong Kong, as Jose said. But then I'm going to come back to the sand. Okay, so how do we describe soil? Could soil be described as a solid? I look at it, people are walking on the beach. Yes, I can think it's pretty solid. So maybe it's just a solid. But then I'm looking at this, and this is material. Okay. With beautiful dry sand of Pilar. This is a beach where I have spent all my holiday with my family since I was born and before. And, well, the sand was flowing, and you could be excused if you thought that sand could be treated like a liquid. And then there is mud as well. So where do soils come from? Well, at the origin of soils, there was rock. And then rock under climate effects, so temperature, rain, fragmented into smaller and smaller bits of rock to different sizes, gravels, sands, silts, and these were transported and by ice, by rivers, by wind, and then deposited, depending on their size, in the riverbeds or in shallow or deep seas. As the soil is deposited, it gets buried, and then it gets solidified, if you want, forming new rock. And this is the rock cycle. Now, all this doesn't happen overnight. It takes tens of thousands of years, it takes millions of years. So this is a very long cycle. A key property of soil, as we see, soil gets deposited depending on how it's deposited and on its size, is the particle size distribution. So we typically look at, what is the proportion of particle of different sizes, and we plot it on a semi-log plot because often the soil can take many different magnitudes of sizes. So that helps us visualize its particle size. We have a strict classification of soils, with gravel being larger than 2 millimeters, sand down to 63 microns. There are silts in the middle, and then the clays are the very small particles, less than 2 microns. Sand is not all the same. There are different sands with different size and mineralogy. So here's a typical quartzitic sand. I recognize the quality, the transparent quality of the sand. This is quartz. But what I can see is that if you thought that sand was all little spheres of rock, this is not the case. They all have their own individuality and their own shape. And then there is carbonate sand. It's made of carbon carbonate. It could be the detritus from marine animals, their vertebrae. But in this case, this is just a coral sand. So what we see is broken bits of coral, and therefore we have holes in the sand and very irregular shapes. So we can imagine that the properties of the two different sands will be very different, and that this one may even be fragile. So before I get to the more technical part, I want to point out some interesting properties of soils. So what Matthew was doing with the sand, well, if you take any sand and you just pour it dry, it will always form a dune with the same angle, which we call the angle of repose. And this is a sort of measure of the strength of the soil. On a large scale, it forms sand dunes, and this is again the sand dune I have the play. I'm lucky to go to on holiday every summer nearby here on the Bassin d'Arcachon, where Clémence is from as well. So we saw some properties of soil. Now Matthew is working on the receding low tide, so the tide is going down and there is water and the water is flowing. And as we see the soil here, the sand is behaving more like a liquid, so we have a quicksand. It can't support the weight as much as it could do before. Okay, sorry for the sound effect. This is by the beach, right? So you can imagine the waves, and this is just beautiful. As soon as you put a bit of water in the sand, it will behave very differently, won't it? And then we can make sandcastle. And if you break a sandcastle, you will see that it is quite repeatable, that it will always form what we call a plane of failure or a shear plane. And we can even try to predict what this shear plane could be with some simple analysis. Oh, sorry. But even though the soil is particulate, we usually treat it as a continuum. Okay, we develop our models based on the fact that we think that soil is a continuum. So we consider not one grain at a time, but an assembly of grain. And actually, one of the difficulties that the soil is triphasic, so it could have solids, water, but also air in it, or some other gas. This is a typical test that we do in the labs. This is our lab at UCL. So we have a cylindrical sample. It's quite large because here we're not testing sand, we're testing ballast. Okay, so rock fragments of 20 to 50 millimeters. They're enclosed in this neoprene membrane, and they're in this big perspex box that is going to be filled with water, and we can apply water that will apply an isotropic pressure on the soil, and we can deviate from the isotropic condition by applying an axial stress and shear the sample until it fails. So this is a typical results that we would get. We plot the force against displacement, and we see how the soil is developing its strength as is being deformed until it reaches a failure load. And that's when it continues shearing or displacing at a constant stress. We can also monitor how quickly the soil is deforming when it is loaded, and that's what we call the stiffness. So a simple model would be saying that the soil behaves like OAC, or elastic, perfectly plastic. But of course, it's quite far from the reality. Even the most common models that are used also in industry are simplistic. An advance in modeling soil would be to consider the different grains, and this is something that some colleagues of me are doing in our department, and this is what we call the discrete element method. So it aims to simulate the particulate nature of the soil behavior and their complex interaction. And this interaction includes, well, it depends very much on the shapes. So some here colleagues in Nottingham University, Glenn McDowell and Matteo is a postdoc, have simulated ballast again. And why do they simulate ballast? So we see some pretty realistic shapes that are mimicked on some model on some samples that they have impregnated with resin and scanned. And the reason is that it's quite difficult to have millions and millions of grain in your model. But also, if you look at every grain is a clump of very small spheres to simulate the shape. So if you imagine it doing it at a very down scale, how much computer power do you need to do that? So it's not systematically done. And in fact, in a lot of DEM model, so discrete element methods, people still use spheres, and they put some what you call rolling resistance to mimic the shape. For modeling soil at the grain scale, we, however, need to know the mechanics at the contact, and that includes normal and tangential loading. And we feel that the texture is going to affect this behavior. So we want to know what are the effects of the grain surface texture. That's going to affect the friction between the particles. And then for some particles, maybe the carbonate sand, there may be breakage, and we want to know how it's going to break and by how much. So if we wanted to create an avatar, so a fake sort of sand, gravel, or ballast, what would we need? The shape, the roughness, the contact mechanics, and the particle breakage. Shape. Well, what do I mean by shape? Shape has, for us, 3 different scales. There's a scale of the form, which is very much a scale of the size of the particle. And here I have 3 rough scale forms. So I have a square, a triangle, a rectangle. And then I have roundness, and roundness tells me about the corner or the angularity. And if I move to this much smaller scale, I have the texture on the surface of my particle, and that's what we call the roughness. So in the old days, people would take their sand and try to compare it to this chart by Powell, and they would try to pitch where is the sphericity, how close to a perfect sphere is the particle, and how angular or rounded it is. So here in the top row, I have all the spherical particles, but we can see that if I go from right to left, I have some corners developing, and here my grain is very angular, even though it has a high sphericity, while here it's very rounded, while the sphericity is very low. Now, as technology has moved on, we do much better. So in our lab downstairs, we have an apparatus where we can, an optical microscope, where we can sort of scan every particle and get a profile. So we can have, for thousands of particles at a time, a projection of every particle and obtain a statistical analysis of the shapes and the size of the particle. Of course, this is in 2D, so it's got some restriction. We can move to 3D. So here, this was work by a postdoc of mine, Hongwei Wang, in Hong Kong, where he performed 3D laser scanner on crushed granite. And you can fit also some sphericity and angularity parameters to your particles. Or you could just use X-ray CT, but you do it at the microscale, so we call it micro CT. And here you have work by Newcastle colleagues. And what you see that the conundrum is how closely to the real shape can you go if you have to simulate every single shape of every particle in your sample. So again, you can think about the computer powers that you will need for that. What about the roughness? So we have tested ballast. This is of basalt from Australia, andesite from China. We have tested granite and we have tested quartzitic sands. And for each of them, with laser, so optical microscopes or confocal laser, we have been able to measure the surface, to get the surface. So this is like a height map of the surface. And the surface that we're looking at depends very much of the scale of the particle. So here, for the quartzitic sand, which is about 1 millimeter across, our surface is 100 by 100 micron. And then in height, we're going to talk nanometers, maybe hundreds of nanometers. Okay, so measurement is nice, but if you don't do anything with it, if you don't analyze it, it's a bit pointless. So I'm going to think more about this surface texture. And first thing I think is, what is this texture? It reflects how the surface is produced. So a simple example is a steel surface, which was produced by cutting. So in this surface, I have a regular waviness. But then if I were to zoom in, I would see a lot more irregularities. And I would talk about long wavelengths for the waviness and the short wavelengths for the irregular features. The waviness is my local shape, and the short wavelengths are my roughness, and both of them form my surface texture. For a grain of sand, I can use a different technique, which is white light interferometry. So this is an interferometer that we had in Hong Kong, and I can determine the surface or measure the surface of this LBS sand. Is actually coming from the north of London, it's Leighton Buzzard. It's a quartzitic sand. And so I can have the whole surface, but if I want the proper roughness and a measurement that is not depending on the shape of the particle, I will try to separate, just here, like the long and the short wavelengths, the shape from the roughness. And even though it is attractive and it's usually a software which is embedded with the analysis of your surface, it's scale dependent. And you may not find, and usually polynomials, so you may not find something that is perfect for your particle. I should also say that sands have these particularities that their reflectivity is quite low, and they are very regular, so it's quite difficult to do those measurements. How could you quantify the roughness, therefore? Well, once you've taken that shape out, you're going to end up with a mean line and then a lot of wiggling around it. And so you can take a root mean square average, and that's what we call SQ, which is one measure of roughness that is commonly used in sands. So in sands, typically SQ is a few hundred nanometers. In ballast, it may be tens of microns. Now, what geologists have told us for some time is that if the geological surfaces have been created by random processes, it's very likely that they're going to be self-similar, which means that if I look at the surface and I zoom in and zoom in and zoom in, I'm going to find similar patterns of the surface. So this is a little schematic diagram showing this. So this is what we call fractality as a property. So if you have, say, a triangle and you divide the triangle in equal triangle and you continue down and down, you end up with a fractal design here. So we think that the surfaces are going to be the same. So somebody who tested it was Valero in the 90s, and he just took one of those 2D projections that you can get from a soil, and he sort of measured the perimeter of the particle by taking different lengths of step. And of course, the more steps you take, well, the smaller the steps, the more steps you need. And there is a power law relationship between the step length and the perimeter, and that defines fractality, this power law. So in terms of roughness, we can link the wave vector, which is the wavelength of the roughness, with its intensity, which we call the power spectral density. And we found a linear relationship if everything's plotted in a double log plot. And this linearity tells us that our roughness is fractal. And so we can determine some parameters to predict what the roughness is, well, to simulate it, including what we call the fractal dimension. And how do we use it? Well, we can use it to reproduce numerically the surfaces we measure. So if this is the surface that we measured experimentally, and we got some parameters, the D and the intensity, we can recreate, of course, not exactly the same, but a statistically similar surface for our analysis. Roughness will affect friction. I'll come back to friction later, but just as a reminder, we haven't invented friction. It's, well before us. Coulomb in the 1900s was looking at friction, and he had a very simple way of doing it. So he had this tray, and he was loading the tray and just sort of measuring how much force he needed to pull the tray. Okay, so this is friction. And that's going to depend very much on the interface between your tray and what's underneath. And if you do that, you find a direct proportionality between your value of T and your value of N. And interestingly, of course, our soil developed the same sort of relationship. So we usually describe our soils as being frictional. Contact. So for contact, the discrete element methods that we use in soils are still very much based in what was developed for engineered surfaces, so nothing to do with geological material, but a very common model is the one that was developed by Hertz for, I think, steel, and this is a model that was developed for spheres in contact, spheres that are smooth and elastic. So, as we've understood, this is not like soil. So, our soil grains are irregular, they're rough, they're not elastic. But how are we going to improve the models? We need experimental data. So we can obtain experimental data in our lab at UCL, as we have a bespoke apparatus to do exactly this, and where we can do particle-to-particle tests. So this is the apparatus. It was first developed at City University in Hong Kong by Matthew, and he reconstructed one here, improved it, and actually now we have two of those apparatus. We have 3 directions of loading, and then we can measure displacements very, very accurately, so very small, and therefore we can test things from ballast, so tens of millimeters, to sands of the millimeter size. If you haven't seen it, you should come to our lab in the basement. So here we wanted to test Hertz model, and this is work by Fatin Al-Tuhafi, who was working with us as a postdoc. So we shaped a natural geomaterial, a granite, as spheres as much as possible, and we control the roughness of the surface as well by milling. And that's what we obtained. So if this is an expression of how the load developed with the displacement, and this is what Hertz would predict based on the characteristics of those granite balls, our experiment, it's still softer, and we think that's because of the roughness, and this is what many people think is the roughness. It's not that roughness is not accounted for in models. There's been plenty of models developed for rough surfaces. It's particularly problematic when you have when you're looking at transmitted electricity. Can't remember how to say. But so even though all of these models are still only developed for engineered surfaces, there's no consensus whether the asperities which form the surface are deforming elastically or plastically, and the assumption is also that the bulk of the surface of the particle is elastic. But that does not necessarily work for highly irregular particles. So here's some tests we've done in Hong Kong. This was Yao Ting, one of my PhD students. So she compressed one particle of sand, 1 millimeter across, against a hard platen. And at each load stage, she would look with the white light interferometer at how the roughness, the surface is changing with the loading. So here we have a very visual example. So these are height maps at 0 to 100 Newton load. And we see very clearly how the irregularities are smoothened out, and the contact area develops and increases with the normal load. So these were, again, this was on the surface of the particle, 100 by 100 microns, so quite complicated measurements to do, specifically trying to see, to replace your particle exactly at the same place to get these measurements. And quite extraordinarily as well, she managed to map the different profiles, and we were able to see that actually the bulk of the particle is deforming plastically under load and not elastically like most models believe. And then this is further work that was done by Saurabh Singh, our recent postdoc, where he managed to put together images of how the sand deforms under load, under compression. So that was beautiful. We've done the same with ballast. And so you do a test where you load, you unload, you take your particle, you do the measurement of roughness, etc., etc. So again, he had some ability with computers. So he was able to look at how the shape of the ballast deforms, and we see how it deforms not just in the contact area, but further down in the bulk. But what was more impressive is that we were able to map the particle contact area, which people usually cannot do, and by binarizing it, we were able, therefore, to find a relationship between the contact area and the load, and we found a linear increase. So this is great for modeling. Okay, so we have plasticity here, and so we can understand better how the geomaterials are behaving. We can also do tangential loading. So looking at fresh granite in basalt, applying a normal stress, and then sort of shearing the particle to and fro over a very small distance of 1 micron. So everything is quite small all the time. And we obtain, up to 1,000 of cycles. And what we see is that there is a stabilization. So it is the soil has the same sort of sliding strength, which we call the coefficient of friction, which is a ratio between T and N, the shear force and the normal force. What we found actually as well is that, of course, there is aberration when you do that, but I won't talk about this. This interparticle friction varies with different sands, and this is work that Vincenzo Nardelli was doing in Hong Kong. So this is great to see how from a ball bearing, which has a very low, so mu is the friction, very low friction here, and is quite smooth, to our quartzitic sand, to the carbonate sand, how the friction is really evolving with the mineralogy and the characteristics of the sand. And what was even nicer is that we could sort of relate this friction to the roughness, the SQ roughness of our particle. And we see how they're all aligning to tell us that as the roughness increases, the friction increases. And this also worked for ballast. And I should just point out that Vincenzo Nardelli also tested Mars regolis, which is a Mars soil simulant, which also aligned with everything. Finally, particle breakage. So yes, particle break, as you will see, they're not completely unbreakable. And how do we map breakage? So this is beautiful work by Chris in Hong Kong and Matthew. And how do we look at what's happening to a soil when it breaks? Well, we start from this particle size distribution that I was introducing earlier, and we're looking at the difference between before and after testing. And you usually find that your particle size distribution sort of rotates up as you have more small particles being created. But also what you see is that the larger particles are not broken because they're cushioned, they're protected by all the smaller particles. And in fact, we have tested, Fatin, again, when she was doing her PhD, has tested these glacial sediments from Langjökull, which we want to retrieve in Iceland. And we should mention that we crashed the Land Rover, the UCL Land Rover, when we did that, actually. But we did bring it back. And whatever amount of compression and shearing she did, we found that there was no breakage. So there is no breakage because, similarly to what we were finding for roughness, fractality has something to say about it. So when the soil crushes in a self-similar manner, which means that, okay, so if you have a cube and it crushes in similar size cubes, etc., you will end up with a whole particle size distribution. And when you finally reach this fractal grading, you will find that all the particles are protected by the other particles. But this doesn't work for all the soils, so there's always some oddities like gap-graded soils. So for sand, yes, sand is challenging because of the size, the shape, the roughness, and much more. And actually, if you wanted to leave now, you could just go and join the talk on Seurat, which is starting at 7 o'clock at the Institut Français. I just found out. Now, clays. So what about clays? So I found it remarkable that when I was trying to look at paintings of soils, I found paintings. It did inspire painters, right? So here we have a painting of a clay stack, a clay from St. Austell, which is in Cornwall, where I also go and spend some holidays. So the clays seem to stack up as sands. Can we analyze them in the same way? Will they be easier to model? Well, they also have different mineralogy. So here's a picture of a clay, elliptic clay, which was actually the clay part of loess from northwest China. So you just reach very small particles. And we see that the clay is made of a lot of different aggregates of illite, mormorillonite. And if you look very close, so here we have 20 nanometers, we can see one aggregate. But I'll come back to it later. But clay can also be made of kaolinite. And the kaolinite looks very different. So often people describe it as looking like book stacked on a shelf. And these are all the particles and not the very, very small scale of 1 micron. And this is another clay with illite and smectite, Lucera clay. And here is more like cabbagey in its manner. The model for clays tend to be phenomenological because clays have got a lot of complexities, time dependency, and saturations. They can swell, they're temperature dependent. And as a result, the models are complex. And some have more than 30 parameters, which is definitely what you don't want for a model. And this is a first incarnation of me. This is my PhD work where I developed this 3 surface kinematic hardening model. And no, it did not have 30 parameters. So how can I study the clay at the microscale if I want to mimic what is so well developed for the sand? Well, I can do experimentally. I can use scanning electron microscopy or mercury intrusion porosimetry. So here, if this is the SEM, I have a tray with lots of small particles of clay, and I can look at them from the top and obtain something which is like this, so I can distinguish domain and think about orientation. With the MIP, I may have some very small samples of clay. I'll explain how you get them later. You fill the container with mercury and you put the mercury under pressure, and that you increase the pressure, you're going to intrude more pores in your clay. And you're going to have a bit of a symmetrical thing to the particle size distribution, what we call a pore size distribution. So here, if this is the intruded volume of mercury, we see here that there's not much intruded, and then suddenly a lot of mercury is going in for these pore sizes, and then it goes in a bit more slowly. And we have different curves for different soils. Numerically, people have tried, so they're still trying to use a discrete Lyman model of the molecular dynamic, as we say, and they're using plates, disks, and spheres. But the problem with clays, unlike sands, it's not the contact between particles which is important. It's because they're so small, it's the charges on the surface of the particle that are going to matter, electrostatic forces. And this is very difficult to model, as well as very small particles. And those particles are not easily identifiable. The interaction is complex. So for example, if I go back to this image, which was taken by transmitted electron microscopy, and so here, this is a little bit of a clay. So what do I make of that? The clay is typically an assembly of clay mineral layers, aluminium and silicon, with some interlayer pores. So we're talking angstroms, nanos, very small. And one of these stacks forms a particle, and this is a particle I can see here. So it's about 20 nanometers across. And then those particles may form some aggregates. So this is my particle here. But I can distinctly see some pores here, and I can also see the pores here. So why not think about pores? Because the particles are so difficult to model and to identify. How could I measure the pores? I've touched on it. I could use nano CT, so nano, one rank lower. That would give me some live images and give me some information about the pore connectivity. Or I can use this scanning electron microscopy for the shape and orientation of the pores, or this TEM to look at the very small pores. If I want, these are just images. If I want to do some measurements, I have mercury intrusion porosimetry. And for the very small pores, I use gas adsorption, typically nitrogen, or some X-ray scattering. So in our lab, what we do, we test our soil. Maybe this is one of our soil samples. We preserve it in cling film and wax. And then we cut it into very small sticks that will freeze dry. And to freeze dry, you put it in liquid nitrogen at its freezing point under vacuum, and then you sublimate the ice. And then you do your test, whatever you want to do. The pore size distribution. So here a bit of technique. This mercury intrusion porosimetry, well, why does it work? It's because mercury has this not wetting quality, which means that if I just put a drop, even if the material is porous, it's not going to wet the material. So I need to put some pressure on the mercury for it to intrude the pore. And by using Laplace-Young capillary law, I can link this pressure to the entry radius to the pore. So of course, I have to assume what will be the shape of the pores, but that will work. And depending on your pressure availability, you can intrude pores down to 5 nanometers. Now I should say that this porosimeter is not here. This is in Paris at the École Nationale des Ponts et Chaussées, where we have some very good collaborators who kindly let us use their facilities. And this is a kind of intrusion-extrusion curve you get. And note that the extrusion is not like the intrusion because there will be some trapped mercury, and that's a defect of this, of the method. So an example of what we can measure, one-dimensional compression, and we typically plot the void ratio. So that's just the ratio of voids in terms of volume to the ratio of solid. And so if you put a sample of soil or clay here in a ring that can deform laterally, and you just load it vertically, its voids are going to decrease, and we usually plot it here against the stress. And so here, because we want what we call post-mortem measurement, we need to take the samples out at every stress level. We need to repeat the test many times and make them coincide to get our different samples. And so if I look at this pore size distribution evolution during this compression, I see here this is how much mercury was intruded against the size of the pores. And I see that first there's a definite decline in intruded amount of mercury, but also all the large pores here are collapsing and some smaller pores are being created. And now, while most people thought in the past that the very small pores that I was looking at inside the aggregate do not deform during this sort of loading, well, actually, when we did some gas adsorption test, we found that the very small pores also deform. And that has inspired France to think differently about their model, which I will show briefly later. We can also look at the orientation during 1D compression. So this is our SCM samples, and we're looking on the vertical plane. So, I was testing that way, I'm looking here. And so I have, for each stress level, a picture of the soil. I sort of delineate the pores, and then I fit them with ellipse, best I can do, and I can get some shape, but also some orientation of the pores. And note that in the next, I'm going to use the loading direction as being the horizontal direction. So at 100 kilopascals, at lower stress, everything's the same. The pores are randomly oriented, but as the stress or the load is increasing, we see a definite direction forming in the pores. Now, what's exciting for us in research is that this was sort of expected, but we can also, in soil mechanics, a lot of our theory is semi-empirical, right? So you just test and you observe, and luckily everything becomes sort of linear on a semi-log scale, or it's fractal. But here we wanted to test the phenomena that form our theory. So I'll give two examples that are a bit beyond. And the first one is going to talk about failure. So again, this is a triaxial sample of clay system, so much smaller, enclosed in a membrane. And we can apply any sort of stresses we want, radially or axially. And we can test our soil to failure. And what you find is that if you do a bit like a sandcastle, so you restrain your soil and you apply an axial load, your soil will fail. And at this failure point, the stress on the soil will remain constant and the volume will be constant. And for many, you can do this at many different stress levels. and you get what you call the critical state line, which is like a failure line. So it's a line which is a location of the failure point of the soil. And the key is that for each of these points, you can reach this point by a number of loading scenario, if you want. So here in blue, it's a scenario where we trap the soil underwater and we shear it, so your sample deforms in shape, but not in volume, while here we allow the water, which is in the clay, to escape, so it's called drained, and it will change volume and shape. And so, okay, so these points are unique in our theory, but it doesn't mean they have the same pore size distribution. So this was work by Yan Hao during his PhD here at UCL, and I must say that any point reached by 4 different stress paths is going to take over a year, because each test is going to take several months, and then he has to take them, degas them, and take them to Paris. So remarkably, what we found is that all these different tests made on different samples and following different history had matching pore size distribution. So here the pore size distribution is plotted a little bit differently. Here it showed me the dominant pore size here. So I can see I have a dominant pore size, and it's the same whatever the stress path I've used. So here I've used 4 at this A point. And though for satisfaction of mind, we did the same for B. And remarkably, we also find that the pore size distribution are coinciding whatever the stress path to reach that failure point. Okay, so we were not going to stop there. So we also tested what happens during this one-dimensional compression. So when the soil is not allowed to deform radially, but it's allowed, but the load on it is vertical. And so we have what we call this normal compression line, which is similar to what a soil experiences when it's being deposited. So you have the vertical load increasing and the horizontal load stress increasing in proportion. So you can reach it by enclosing your soil in a ring and then increasing the load. Or if we use one of our triaxial apparatus, we could actually do an isotropic compression followed by a pure deviatoric shearing. So we have 2 paths to reach those points C, D, and E. And here we look at how the void ratio is decreasing, is changing as well during this test. So along the path with the odometer test, so this is similar to the 1D compression I showed before, we have C, D, E. The total intruded volume is going to decrease, and then there's a little bit of a shift with the main size of pores. But what's remarkable is that, again, taking totally different samples, different stress paths to reach the same point on our state line, our normal compression line, we found some coinciding pore size distribution. So that's still get us thinking, and we're trying to think how we can improve the models with what we found. It's still quite recent. So this work is being continued by Richard, who's a current PhD student, who's just submitting now. And so here we're testing wetting, because wetting is very important when you're thinking of clay, engineered clay barriers for landfills, and also as a buffer for nuclear waste geological disposal. So here we tested a clay, I think kaolinite, this one. And so this is a normal one-dimensional compression. And then he also took the clay completely dry as a powder and compacted it, and then wetted it until it reached under a controlled stress, the same point A. So it's always the same trick. We're trying to reach the same point. And what you can do is to otherwise compact it dry and wet it at a controlled volume. And okay, the story is the same. We found 3 coinciding pore size distribution. And you always have to try it again and again. And for 3 different points, we found the same. So that was beautiful to see. And this sort of buffer that people are looking at for burying canisters full of nuclear waste, it's also, we want to know how the clay may swell. So here we looked at the length of swelling of the clay and how it changes the pores. And here what you find is that the longer the path of swelling, of course, you have a change in the pore size distribution, but more remarkably, Schwab also did some X-ray scattering tests. And so he also found some changes in the very small pores. Look here in terms of angstrom or nanos. So sands, I think, are best described by grains, and clays are best described by pores. So what next? Well, we have colleagues in Tsinghua who are very lucky to have been given a few grams, very few, of lunar soil from the near side and from the far side. So with these very few grains, what do? They look at particle breakage. Mind you, they were only allowed to break one grain because they have very few. And they look at particle shape, okay, because they want to know how they're going to create an avatar, because nobody can test, we have our soils, we can be, we can test it, we can get our soil, but the lunar soil, you can't test. You couldn't fill one of our triaxial experiments. So you need an avatar. And what about the clay? Well, Angelo Amorosi, currently at La Sapienza, good friend now, has been really inspired by our work. And he has is developing, this is very hot the press, a new generation of micro-informed thermodynamics-based constitutive model for clays, where we have our little aggregates, intra-aggregate pores between the aggregate and the orientation of the aggregates. So that's done it for me. So that I've put a collection of people here. Marion Craig, you're down here, my brother, and thank you very much.
Thank you very much, Beatrice, for an absolutely fantastic presentation. I think that we are all extremely glad that you decided not to be a doctor and dedicate yourself to work with sands. And it's been absolutely wonderful how you've been able to, walk us, from basements to the moon. And so thank you so much for the great presentation. We have a few minutes for questions. So please, if anybody has a question. Well, I might start with one. One was that you showed the sandcastles and you show Matthew walking in the sand. The role of water is one that I find fascinating in this whole concept. And of course, you showed it with the sand. What about with clay?
With clay? Well, clay can also be clay can also be what we call unsaturated, but clay, because of the surface charges on the particle, will have the more cohesive nature to them. So in sand, you rely on the fact that there is water, but not too much to hold the particle together by what we call suction, while in clay, you will have some bonding between particles, which doesn't require this necessarily. So you don't find clay as dry powder, per se, in the ground, yes. Yeah.
Yes.
First of all, thank you. Hi, my name is Bruno Delgado. First of all, congratulations, Professor, for the brilliant presentation. I am very enthusiastic with this subject, and I would like enjoy, because it's my first time here in UCL. I will enjoy to make a question maybe, and it's involved some research from you and maybe Professor Koop as well. That is, of course, a curiosity, because we are studying a lot of things, and you can see some behavior in compare with another results, of course. I am curious about the transitional behavior, for example. If you have some measurement about what occur in the microstructure at the particle level that condition this transitional behavior, because it needs occur something. This is why I'm sorry, because I can see that's a little out of your main subject, but not completely out. Can you see my?
Yes. I think this is a topic that, yes, people and yes, Matthew's group have tried to elucidate, and the only microstructure analysis I can think of is the one that Tedesco have done. So Tedesco, who was a PhD student in Hong Kong at City University, she tried to, so she did some tests. So a transitional soil is a soil which has a mixture of particles. Often maybe it can be gap graded, so some small particles mixed with some big particles. And what I've shown about this beautiful line being sort of unique for the soil, well, they can have different lines that will depend on their depositional history. And so that's the tricky bit that people are still trying to elucidate. And they have done some tests where they preserved some sample, I don't know what, in compression, in what? In everything, and taken them to Paris, our great friends, and done some MIP data. So maybe we can give you a paper to look at that. But otherwise, yes, people, it's still case of my soil's transitional. This one is not. This one is not. But there is some work to do. Yes.
Thank you so much.
Can you go?
Perfect. Thank you so much for this very interesting presentation. I joined the first half online, but it worked perfectly also online. So thank you so much. I was wondering regarding the offshore wind turbine foundations that you mentioned in the beginning. And I think that the examples you provided regarding sand and modeling sand foundations could also help informing designing better offshore wind foundations. I was wondering if you could expand a bit on that point, because I think that's also very exciting and innovative area.
Yes, I know that there is some DM and maybe work, maybe even Helen in our group has been doing some discrete element modeling of pile foundation subjected to a range of loading. So the complexity is that if it's offshore, you're going to have a lot of random events, and your pile is going to be subjected to cyclic loading due to the waves and the winds affecting this. The complexity with full-scale simulation of using particulate approach is how can you simplify the problem? You cannot simulate all the grains, so it's always there are some ways to do it, but you will always sacrifice something: the shapes, the number of particles, the real surface of your piles, etc. But it has occupied I think colleagues in Oxford and Imperial for over 10 years of research. Now, the recent times, they've just had a couple of big projects finishing. So it is a subject of research still continuing now. And for those who want to approach a problem of wind turbines without thinking of the foundation, I think they should try still to talk to geotechnical engineer. Yeah.
Thank you for the talk. I had a quick question. You showed a slide with the PQ space and the critical state line and the stress paths, and then you followed that up with a plot of a peak in the grain size. I don't think I fully followed that. Was it that the grain size distribution was the same no matter what the stress path?
Except it was a pore size distribution.
Okay.
So these were so yes, so whatever the stress pass on that critical state line. So the critical state line, we had a point, and you could reach this point with a variety of different loading paths. And then at the end of each of the loading paths, we preserve the sample. Then we cut smaller samples, freeze dry them, and analyze them by mercury intrusion porosimetry. And so we got the pore size distribution. And all those independent samples that reach the same point showed to have the same pore size distribution at different stress level as well.
Okay. So the critical state line, all the critical states, so at the point of failure, you could see that all the pore spaces were the same.
Yes,
okay.
The distribution of the pore size, yes, of the pore space was the same in terms of sizes of pores, yes.
Okay. Yeah. And from that, you could tell that it was still shearing at this without changing volume.
That's right. So yes, yes. So in a way, you could say a given void ratio at a given state gives you a unique pore size distribution, but we're still looking into that. Yeah.
Thank you.
So I think yes.
Drink time?
I wanted to invite you all for the reception outside in the coffee cafeteria area. And once again, let's thank Beatrice for a wonderful